Hello, Tensor friends. We're going to wrap up our discussions of Gaussian curvature. So what we did last time was we derived this relationship, which is a tensor equation, works in any coordinate the system, which is the second derivative of a position vector with respect to arc length is given as this, and the magnitude of this vector, that's a vector, is the Gaussian curvature. Okay, so this basically works for a flat manifold. So you're trying to understand the curvature. You've got some curve on a manifold, and the manifold is flat, and this works great. But beyond that, it's very difficult to use. So now we're going to look at a curved manifold. So we're going to look at the Gaussian curvature of a hyperbolic paraboloid using first and second fundamental form. So this is old school stuff here. And after this, we'll compare it to the modern way, which would be to use the Gaussian curvature tensor. And then after that, we will look at it using the Riemann curvature tensor. Okay? So here's our function, x squared minus the y squared. So the constants are just 1. All right, we're going to parameterize this thing, and we're going to start with the second fundamental form. Okay, so our parameterization is going to be x equal u, y equal v, and then z is the function x squared minus u squared minus v squared. Okay, so now we can write a position the vector with u ex plus v ey plus this ez. Okay, so what we're actually doing here, and we're going to look at some graphs, the graphics of this, is we are embedding a surface, a two-dimensional surface, in a three-dimensional space. And the three-dimensional space is the Cartesian space, and it's called the ambient space. Okay, so we have a two-dimensional object, it's called the submanifold, into the ambient space. Okay, so here is their terminology of the old days. So R sub u is the derivative of this position vector with respect to the first parameterization, which is u. So that's obviously just 1 here. There's no u here, and this is 2u. And I'm writing this down here because we're going to use this later. Okay, and then RV is the derivative of that with respect to v. So we get 0, 1, minus 2 out of here, right? I'm sorry, minus 2v. Okay, now this is also the same way we would find the basis vectors, and we would call them EU and EV. This is just old school, the way my old books have it. Okay, now we're going to take the second derivative of these with respect to u, and they call those R sub UU. Okay, so the second derivative of this with respect to u is just 2, and the second derivative of the derivative of Ru with respect to v is 0 because there's no v in it. The derivative of Rv with respect to u is also 0. There's nothing in it. And then the second derivative of r with respect to v is just minus 2, right here. All right. So now we have what we need to set up this odd-looking thing. So they call this the quadratic form. So this is the way the Gauss and his contemporaries would write down the second fundamental form by calling it the quadratic form. Okay, so we have the L, M, and N components, and you'll see what those are later. All of them are dotted with the normal. All right, the normal. Now, how are we going to find the normal? Well, it is normal to these two basis cell vectors. Okay, let's go look at all this before we go much further. Okay, so here's our manifold. This is a hyperbolic paraboloid. And the reason I chose it to work on is because the basis vectors on here are they're just crazy. They're all over the place. They're not orthogonal and they're not normal. So it's just the opposite of most of the work that we do. Okay, so by using that parameterization, I can pick a point on here. Okay, there's the point. I can move it up and down. I can put it anywhere I want. Okay. Now, at that point, I can define the basis vectors that we just showed. and they look like this. Now they're very well behaved here. You can see that because it's at 0, 0. But if I move off of 0, 0, then they go insane. They start pointing in all kinds of different directions. Okay, so let me put it back because it makes it easier. Ooh, I'm not very good at this. The sliders. Okay, now if I take the cross product of those two basis vectors, I get my norm. So that's what we're talking about. There's the normal to the surface, and obviously the normal moves anywhere they move, and it's trying to maintain sticking straight out from whichever the point you're working on. Okay, let's get back to the doc. Okay, we want to find our normal so we can take these the products and complete this little matrix here. Okay, so how do we do that? Well, like this. So you write down your basis vectors in the top row. This is RU because I'm crossing it first, and this is RV. Okay, so you block this out, you block that out. That's your EX. It's going to be the component for your EX. So it's the determinant of this little guy here. So it's this times this minus that times that. So you get a negative 2u. Block this out, block that out. Write down a negative sign. Don't forget that. This is your EY component. So it's 1 times this minus that times that. So you just get a negative 2v. The negative makes that negative positive. Last one is this one. The EZ component is this determinant here, which is just 1. Okay, so there's our normal. And here I've rewritten it. Okay, so now we can go do the products that we needed. So we need to take the dot product of RVV with the normal. Okay, so RVV was what? Minus 2EZ, and we're dotting it with the normal, which is just the only EZ component here is 1, so we get a negative 2, get 2. The M 0, and the N is negative 2. Okay? Now here is the matrix. So we've got L, M, M. These are always equal. N. All right. And the determinant of that is this times this minus this times this. So it's a negative 4. All right. Now we want to do the fundamental form. Now, the way they did it in the old days was just too long, and it's now called the metric tensor. Okay, it's called the metric tensor, and we know how to do it, and it's easy. So let's just do it the modern way. So it is that the GUU is RU.EU. This is RU.RV, RV.RU, and RV.RV. Okay, and we know how to do that. So we dot these two together. We get 1 plus 4u squared. We dot these two together, we get negative 4uv. And it's a symmetric matrix, so GVU is the same, right? And RVV is RV.RV, so we dot those together and we get 1 plus 4v squared. Okay, so we've got our first fundamental form, they call it, and we would call this GIJ. All right, so here's our metric, the tensor. And what is the determinant of this? Was this times this minus that times that. Okay? So it's this times that minus, and it's a negative times negative is a positive, and then you got a negative, so it winds up a negative. So we FOIL this, and we get this, 1 plus 4v squared plus 4u squared plus 16u squared v squared, which cancels this one. So that's lucky. So we're just left with this, the determinant of that. So in the old school days, the Gaussian curvature was defined as the determinant of the second fundamental form divided by the determinant of the first fundamental form. And you got this. Okay? Negative 4 over 1 plus 4v squared plus 4u squared. And the maximum curvature for the function we're working on, the hyperbolic paraboloid, is when u and v equals 0. So let's go take a look at that. Okay, so right now we've got our parameters u and v set at 0, 0. Right there it is. And here is, why did I call that K2? I don't know. Here is the Gaussian curvature, and it's a -4. Okay. And if you move off of this either that way or that way or this way or that way, let's go back up here to 0. And then I'll move the other one around. You can see that the maximum curvature is always down here at 0, 0. Oops, it's not quite 0, is it? Right there. Okay? So that's the way they did it in the old days. I'm going to stop here and maybe I'll go check the time and we'll do part 2. We'll do the Gaussian curvature tensor because it's a little bit complicated. Okay?